And now for our last lesson, the significance test for slopes. And we're going to revisit the spring example where we had the different masses suspended from the spring. And we had done a confidence interval for the slopes in the previous lesson. So the question is, sometimes when you're looking at a scatter plot, you may think there's a pattern when in reality there's not. So how do we mathematically show that there is a positive linear relationship between the spring length and the mass? Now, admittedly, in this particular example, it's pretty obvious, but the math we do here works for any of the problems we would do. So first of all, we're still going to have a null and alternate hypothesis that has not gone away. And the null claim is usually that there is not a correlation between the two variables. Do not confuse correlation with causation. We're just talking about correlation in this lesson. And so we would say that beta 1, which is our population slope value, is the hypothesized slope. And it's usually 0. The claim that there's no relationship would mean that it doesn't matter. We just have a flat line going across. Now, the three forms the alternate hypothesis can take are that the slope is negative, the slope is positive, or the slope is just not equal to 0. Usually, I have the feeling we would end up doing one of the first two forms of the test rather than the last one. So in our example, our null is that the slope is 0, that there is no relationship between spring length and mass. And our alternate, we're going to say that it's positive because that makes sense. If I suspend more mass from the spring will extend more, and that will give us a positive relationship. So beta 1 is the slope of the regression line relating the y, which is the spring length, to x, which is the mass suspended from the spring. Please be sure when you're doing your hypothesis to say what the variable represents. Don't just give me these two lines. You get dinged for that. Okay. So the test name we're running, it's called a t-test for the slope. We're not doing a z-test. We've never done a z-test. And because we have some, our sample sizes tend to be smaller, that's why we do a t-test. Just the same way we used a t-interval for the confidence interval for the slopes. The conditions are exactly the same. It needs to be linear, independent, normal or nearly normal, equal standard deviation or equal spread when you look at the residuals, and random. So we had already checked the conditions for this example, so you can refer to the previous lesson if you forgot how we did that. Just as we've done in our other significance test, we're going to calculate the test statistics. It's going to be a t-test. And it's similar to what we did with the means. Basically, it's going to be your hypothesis, B1, which is the slope you got from your measurement, minus your hypothesized slope, which is almost always 0, divided by the standard error for the slope. So I actually have highlighted the slope and the standard error for the slope. If I calculate the test statistic by hand, you can see it's 4.9790 minus 0.119, or 41.84. By the way, that's really close to that t-value, and I think the only reason you see any difference at all is there's some rounding going on here, and I use rounded values. So a lot of times, honestly, you're not going to have to calculate this by hand. You might, but it's frequently on your computer output right there. So now you use your alternate hypothesis to determine how to shade the t-distribution and show what p-value you are seeking. If it's a left-tailed, so if you're looking at a negative slope, you're going to shade to the left, and you're going to take in whatever your test statistic was. Your left boundary, because you're starting way over here, is going to be negative infinity, and you'll go to whatever your t-value is. For a two-tailed, that means you have both sides shaded. So we can just calculate this left one and multiply it by 2. So we'd have that. So our left boundary would be negative infinity to t. And then for a right-tailed, it just switches around, and it would be, whoops, that should be over there. And it would be t to positive infinity for a right-bounded one. To calculate the p-values, you would press second distribution, scroll to tCDF, and you would enter in your left and your right boundaries and your degrees of freedom. So this is just like we did before. Notice, though, that the degrees of freedom for linear regression is n minus 2, not n minus 1. So if I did the p-value here, tCDF of 41.84, because I'm looking at a positive slope to infinity, my degrees of freedom are 12. I had 14 data points. I get a very tiny number. all right? By the way, here's your output for the p-value, all right? And that is basically 0. And you can argue 1.067 times 10 to the minus 14 is pretty darn close to 0. So you usually won't have to calculate this by hand. It will normally be on your computer output or on the calculator output. So conclude is the same. Because of our p-value, it's either greater than or less than. And remember, it doesn't have to be 0.05. It can be a different alpha level. We either fail to reject or reject, depending on the value. And there's either insufficient or sufficient evidence that the true slope of whatever it is either greater than or less than or not equal to. So in our case, we're going to say with a very low p-value of 0, which is less than our alpha of 0.01, we reject the null hypothesis. We have strong evidence that there is a positive linear relationship between mass and spring length. And that totally makes sense based on your physics classes. Now, we can also do a t-test using a list of data. So just make sure you have your data entered in the list using stat edit like you've been doing all year long. Press stat and test to get to this menu, and then scroll down to F line reg t-test, which is linear regression t-test. X-list is your independent values. Y-list should be your dependent. Frequency should be 1 in almost all situations. And beta and rho, select the one that matches your alternate hypothesis and then scroll to calculate and press enter. Then you'll have your output screens here. The third line is interesting. There's your test statistic. There's your p-value, and there's your degrees of freedom. So that should give you enough to come to a conclusion on your test. Now you'll notice there is a row there, and what is that? That actually represents the population correlation coefficient. Remember, it can take a value from -1 to +1. And so when we say positive slope, our correlation should be positive. So we're saying rho is greater than 0. And if we say negative slope, our correlation should be negative. So we would say rho is less than 0. So they're always going to match right there.